Welcome to lesson 2. The name of this lesson might sound a little bit familiar because we had a multiple representations lesson last unit, but this time it's going to be with functions. There are 4 different ways to represent a function. We can do it with ordered pairs, a table, which is really similar to ordered pairs, a graph, which is a visual representation of ordered pairs, and a mapping. So in this lesson, we're typically going to be given one of the representations and asked to fill out the others. So in this case, I have the ordered pairs. I'm going to take each of the inputs, which are the x values in each ordered pair, and I'm going to list them out in my mapping. Now I would prefer to have that in numeric order, so I'm going to do that. All right, now I'm going to take the 4 y values, 1, 5, 7, and 2. Again, I'm going to put these in numeric order. Now I'm simply going to draw an arrow from each input to its given output. 4, 1 tells us that the input of 4 goes with the output of 1. So I'm going to draw an arrow from 4 to 1. 3, 5 tells us the input of 3 goes to the output of 5. Draw another arrow. 8, 7 tells us that 8 goes in and 7 goes out, so 8 goes to 7. And finally, 6, 2 tells us that 6 goes to 2. This is a mapping of that same function. For the table, I really can just copy over those ordered pairs, 4 and 1, 3 and 5, 8 and 7, and 6 and 2. Now I'm going to take these points and I'm going to graph them. So for 4, 1, I go to an x value of 4 and a y value of 1, and I plot that point. 3, 5, I'll go to an x value of 3 and a y value of 5. In case you're having any kind of tough time graphing, this is the x of 3 and the y of 5, and I plot my ordered pair there. And then I'll do the same thing for 8, 7. Which forces me to go off the graph a little bit, and then 6, 2. Some people try to go and connect the dots here. There's no need to do that. We just leave it as it is. And now I've got my 4 representations of a function, and I'm asked, is this a function? Well, remember from the last lesson, we need to make sure that no input is going to more than one output. I think the easiest way to determine this is by looking at the mapping. I don't see any one input with 2 arrows coming off of it, so no inputs going to 2 different places. That means that this is a function. All right, so this time we start off with a mapping. We see that -6 goes to -4, and it also goes to -2, and then we see some other ordered pairs. Well, they're not written as ordered pairs, but now we can turn them into ordered pairs. Since -6 goes to -4, we can write that as -6, comma, -4. And then we can also write -6 going to -2, -2.5 going to -2, 1.5 going to 0, and 2 going to 5. And now we've got 5 ordered pairs coming from that mapping. With those ordered pairs, I'll be able to fill out the table. I did need to extend a little bit there. And now we'll turn those ordered pairs or the table into a graph. -6 going to -4, -6 going to -2, -2.5 going to -2, 1.5 going to 0, and 2 going to 5. Now again, they ask us whether or not this is a function. This time the answer is no. We can see that in the mapping from the 2 arrows coming off of one input. One input is only allowed to go to one output, so this situation means that we do not have a function. We can also see this by repeating inputs in both the ordered pairs and the table. If you ever see a repeating input with different outputs, that means it's not a function. All right, on this one, we're given a graph and we're expected to get the others. I just really want to focus on getting the mapping. In order to get the mapping, we're probably going to generate ordered pairs anyway. So this point right here has an x of -4 and a y of 2. So its ordered pair would be negative 4 comma 2. This guy right here has an x of 1 and a y of 2, giving it an ordered pair of 1 comma 2. This guy right here is at 4 comma 2. And this last one's at 6 comma 2. Now that we see all those ordered pairs, if we just go left to right, we should be able to get our x's in numeric order. So negative 4, then 1, then 4, then 6. I'm just listing the x's that I see below in my ordered pairs. And now for the y's, to get those in order, you would just go from the bottom up, but they all happen to be 2. And we don't need to write 2, 2, 2, 2. Instead, we can just write 1, 2, and have all of these arrows point to the same place. That would be the appropriate mapping for this unique situation. And now they ask us whether or not this is a function. I would say yes. Even though there's a big cluster of arrows in the same spot, what we notice is every input only has one arrow coming off of it. That means that this is a function because no input has multiple outputs. All right, the last thing we're going to learn about is called the vertical line test. So we're going to be asked the same question of whether or not something's a function, but we're going to do it using a graph. Now, how do we answer this question when we can't see the inputs or outputs? Well, with a graph, we actually can see the inputs or outputs. So if we look at a graph and we look at a particular input, let's say 1, any point on the vertical line through 1 would be an output that goes with an input of 1. So this point here on the graph would have an input of 1. And if I went to negative 2 and drew a line, any point on that line would be a point that has an input of negative 2 because it has an x value of negative 2. So a vertical line can represent all of the possible outputs for a given input. Now let's look at a different curve. For this curve right here, if I take a vertical line and I run it through this function and it hits the graph in more than one spot, like in this case here and here, that means that this is not a function because this input, whatever input's right here, has 2 outputs, one here and one here. And we know that any given input can only have a maximum of 1 output. So let's look at a formal definition of the vertical line test. It says that if a vertical line touches a curve in more than one place for a given input, then the relation is not a function. So this is an example of something not being a function. The opposite is true. If the vertical line will never touch the graph in more than one spot, then it is a function. So let's take a look at these 3 problems. While it gets pretty steep here, this curve is never touching the vertical line in more than one place. As I run it through, there's always exactly one place for which the line is hitting the curve. That means that, yes, this is a function. This is a visual way to determine whether or not something's a function. Let's do this example. As I go through, the vertical line is never touching this line in more than one spot, so this is also a function. Now let's try this example. As I slide the vertical line, we notice right away that we are contacting this curve in more than one spot, meaning no, this is not a function, and all we need to say for our justification is VLT. The vertical line test says that no, this is not a function. There is somewhere on the graph where a vertical line can hit the curve in more than one spot, meaning it is not a function. All right, in this lesson we learned that we could take one representation of a function and generate any other type of representation. Then we learned that we can determine whether or not it's a function either using the vertical line test or just looking at the mapping and looking for 2 arrows coming off of one input. If you came away with anything else, write that down now. Otherwise, we'll see you next time.